Okay, let's talk about periodic table basics first before we actually get into the quantity known as moles. Here's periodic table. We've talked a little bit about it so far in class, right? We've got our atomic number, which is equal to the number of protons. For a neutral atom, it's also equal to the number of electrons. We also have our average atomic mass, and that's the weighted average of all of the naturally occurring isotopes. Okay. But there are regions of the periodic table that we should be aware of, where the metals are located, and that is to the left of that staircase. Flipping back real quick. That is, all of these are metals. And then to the right of the staircase are the nonmetals. Also includes hydrogen. Hydrogen is over here kind of with the metals because it is really a unique element, and it has, there's reasons why it's in the first column that we'll get to when we talk a little bit more about the periodic table. And then just because you may be wondering what the staircase is actually called, these are known as the metalloids. Okay. Now when we start to write chemical equations, we need to know how to represent. How do we write these different elements when we want to write like a chemical equation? Okay. Well, for metal atoms, we just use the element symbol. So for instance, sodium would just be represented with a Na, its symbol. Iron, Fe, that's its chemical symbol. And copper, Cu. There's also things that just have one letter, and that's tungsten. It is important that you note that the first letter is capital, the second, if there is one, is lowercase. And that's uppercase for the first letter. If there's only one, then it should be written in uppercase. There are 7 diatomic elements: hydrogen, nitrogen, oxygen, fluorine, Cl2, chlorine, bromine, and iodine. Those are diatomic elements, meaning as they exist as an element, they are bonded together to make a molecule that is 2 atoms joined together. So memorizing those 7 are very important, so that when you just hear that oxygen reacts with hydrogen, you know that the oxygen they're talking about is O2. The hydrogen that they're talking about is H2. This is only when they are elements. Okay? Only when they are elements. You can also have hydrogen atoms, which we would write just as an H. You can also have any of these elements by themselves or a single atom in a bond. For example, I can have one hydrogen bonded to a chlorine. Okay, they do not have to come in pairs, but if I'm talking about any of these 7 as elements, they are diatomic elements. They exist as an element as 2 atoms bonded together. Ionic compounds, this is something for the future, is a combination of a metal and 1 or more nonmetals in a compound. Important to note is for these compounds to come into being, there has to be a transfer of electrons, making 1 cation, 1 anion, or more, and that then these 2 oppositely charged ions would be attracted to each other, making a compound. For covalent compounds, there is sharing of electrons, and that is where we get the molecules such as hydrogen or something like water. Okay, and these make molecules. So If we look at a recipe for something, and this I'm hoping that maybe you recognize as being for chocolate chip cookies. We measure things using cups, teaspoons, or large eggs, items, or masses, depending on if they come in a can or a bag. And that's how we measure things. They're based more on convenience. How easy is it to measure that using a cup or a teaspoon, or if I have to count them, something like eggs, okay? Count them. When we look at a chemical equation, it is a kind of recipe. And the units that we use for these recipes are molecules, is one. So for the equation as written here, 2 molecules of hydrogen react with 1 molecule of oxygen to yield 2 molecules of water. Now, if we actually use molecules, think about the size of molecules. If we're going to count them, it's going to take a long time to count even enough so that we can actually see it. So we're going to have to use something else to count them. And we're going to use what's called a mole. A mole is a count. It's like a dozen, in that a dozen, 1 dozen, is equal to 12. I can have like 12 items. I can have a dozen muffins, I can have a dozen eggs, I can have a dozen poodles, I can have a dozen people. 1 mole represents 6.022 times 10 to the 23rd representative particles. So it represents either a iron atom or 1 mole of hydrogen would represent 6.022 times 10 to the 23rd molecules. Okay? This number is known as Avogadro's number. And we use this mole, okay, to represent the items that would be reacting in a chemical equation, molecule or a atom. But we need to be able to convert from this count to a more useful unit, something that we can actually measure in the lab, like mass or volume. So the first thing that we have to do is what are these representative particles? How would we draw them? For an element, again, the atom would look something like this if I was drawing it. If I were writing it in a chemical equation, I would just write it like that and probably put in its state of matter. This, in parentheses, means a solid. If I was writing a diatomic molecule, oxygen, oxygen happens to be a gas. Okay? If I were drawing it, I would draw it like that to represent 2 atoms joined together in a chemical bond. Okay? So for a covalent compound, the representative particle is a molecule. For an ionic compound, the representative particle is called a formula unit. And we'll get into that in a little bit when we talk more about bonding in a future unit. Okay. So, looking at this equation, if I were to read this, say 4 atoms of iron plus 3 molecules of oxygen will react to form 2 formula units of iron 3 oxide. Okay, a formula unit representing an ionic compound between a metal and a nonmetal. Okay. Now, we can also use this chemical equation. We could have said 4 dozen iron atoms react with 3 dozen oxygen molecules to produce 2 dozen iron 3 oxide formula units. Well, we're not going to count it in dozen either, but if we do say 4 moles of iron reacting with 3 moles of oxygen yield 2 moles of the iron 3 oxide. This mole gives us a quantity that we can actually measure. This is measurable in the lab. And that's why we would use the quantities mole. Why is it so large? Because the atoms are so small, we actually need that many to give us a mass that's big enough to weigh. And that's typically how we will measure reactants, is using the mass balance. So how big actually is a mole? Enough soft drink cans to cover the surface of the earth to a depth of over 200 miles. Whoa. If you had Avogadro's number of unpopped popcorn kernels and spread them across the United States, the country would be covered in popcorn to a depth of over 9 miles. That's a huge number. And if you were able to count atoms at the rate of 10 million per second, it would take about 2 billion years to count the atoms in 1 mole. So hopefully that kind of reference gives you an idea of why we need a mole to be so large, and an appreciation for how small atoms actually are. Okay, so how do we relate these moles to the periodic table? Coolest thing ever. The mass of 1 mole of an element is equal to the atomic mass, that's on the periodic table, remember that is the decimal number, using grams as the unit. This is called the molar mass, and it's the mass of 1 mole. So if we were to look at the molar mass of oxygen, we would say it is equal to 16.00 grams per mole. That's the grams in 1 mole. For example, 1 mole of carbon has a mass of 12.01 grams. Another way of saying this is 6.022 times 10 to the 23rd atoms of carbon have a mass of 12.01 grams. So what's the mass of 1 mole of calcium atoms? Perhaps you should get the periodic table. I look at calcium. Oops. If I look at calcium, 40.08. So to answer this question, what is the mass of 1 mole of calcium atoms? It is 40.08 grams. Calcium. So, remember representative particles. Most elements on the periodic table can be represented as elements just using their symbols: sodium, copper, chromium, neon. The first 3, the S in parentheses, mean they're solid at standard states. Neon is a gas because it is a noble gas. There are 9 other elements. I'm going to add 2 more to the 7 diatomic elements. Sulfur as an element is commonly taken to be in a molecule of 8 sulfurs together. Phosphorus is usually taken as a P4. They both exist as solids, S8 and P4. You should know that those are the elements, as you should write them if we have sulfur or phosphorus in a reaction. All right, so, how do we handle diatomics? Well, looking at the periodic table, what is the mass of 1 mole of oxygen atoms? Well, 1 mole of oxygen atoms is 16.00 grams per mole for oxygen. What's the mass of 1 mole of oxygen molecules? Well, you know that oxygen is O2. So if I have 1 mole of these bonded together, if one of these is 16 grams per mole, and I do mean to write 16.00, it means the second atom, if I have a mole of them, would have a mass of 16 grams per mole as well. So overall, this is 32.00 grams of O2 in 1 mole of O2. All right, so let's get down to some math. Let's calculate the number of moles in 4.3 times 10 to the 24th atoms of sulfur. All right, well, I'm going to start with the given. Whoops. 4.3 times 10 to the 24th atoms of sulfur. So it's not S8, it's just S because it says atoms of sulfur, times, well, moles. I want to end up with moles. How do I relate atoms to moles? Well, remember, moles is just a number of things. So it's 6.02 times 10 to the 23rd atoms of sulfur in 1 mole of sulfur. So if I get my calculator out, in my calculator, I'm going to do 4.3 EE, that EE button on your calculator, 24, there's no times, no 10, okay, and then divide by 6.02 to the 23rd, I get as a number 7.14286 times 10 to, oh, I don't get a times 10. Nope, I just get that number. All right, now I need to round it because I got to pay attention to significant figures. This number has 2 significant figures in it. This is taken as a exact number, so this actually has infinity. So I need to round this to 2, means I need to round it to this place. Looking at the digit behind it, that's 5 or less. So it should be 7.1 moles of sulfur. Now I want to calculate the mass. Okay, so I have 4.3 times 10 to the 24th atoms of sulfur times 6.02, I'm going to say 22, times 10 to the 23rd atoms of sulfur in 1 mole of sulfur times, now I can relate moles to grams from the periodic table, and it's 32.06. This is from my PT table. Putting this in the calculator, 4.3 EE24 divided by 6.022 EE23, no times 10, no time 10, blah, and then multiply that times 32.06, and I get 229 grams of sulfur. I'm going to have to round it to 2 significant figures, so I should put my final answer as 230 grams of sulfur.